The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
I'm going to take a step back and talk a little bit about the first part of the chapter in the guide that addresses the objectives of protective systems for reinforced concrete structures. The goals of these protective systems include improving the durability of a concrete structure, enhancing performance of structures that are exposed to corrosive environments, extending the useful life of repairs, and this is achieved by limiting the intrusion of moisture, chloride ions, carbonating agents, and other chemicals or contaminants that may contribute to the corrosion of the reinforcing steel or other metal embedments within the concrete. Ultimately, this will reduce or eliminate the corrosion of steel, which eventually leads to damage of the concrete structure. This is applicable to all protective systems, including those that David just described, the electrochemical techniques. So some of the repair issues associated with concrete that can be treated with these protective systems include low cover, poor quality of concrete, misplaced steel, water leakage and penetration, which eventually will lead to corrosion of the reinforcing steel, and the damage that you can see right here. In the upper section, you see a soffit of a concrete structure that has been corroded as a result of very low cover, and you can see the damage. Carbonation is also an issue, and David showed a few pictures using phenolphthalein. You can see right here, this is an area that has been carbonated. You can't tell, except that there's been damage. There's some cracking. We use a solution called phenolphthalein, which is a chemical indicator. It changes color when it reaches a pH of around 10. And what you can see right here is that this area that is clear is carbonated, and the area in red is not yet carbonated. This is an indicator that the carbonating front is actually penetrating from the surface towards the interior of the concrete. In addition, other issues include anodic ring effect, and that occurs when repairs are conducted on a concrete structure that may already be contaminated with either chlorides or CO2. And by introducing a new mortar material or new repair material, which is not contaminated, you may be creating accelerated corrosion cells that take place on the exterior portion of the repair. Hence the name ring effect, because it takes place in a ring fashion around the repair. Those can also be addressed with protective systems. And of course, surface erosion, eventually damaging the surface of the concrete due to traffic or constant wear. The selection of the protection systems needs to be carried out, taking into consideration a holistic view of the structure. There are some important factors that are structurally driven that help us determine which is the most appropriate protective system to be used. And that may include the type of concrete that is being used, both on the surface and in the bulk, the exposure, environmental concerns. There may be restrictions. There may be locations where maybe confined space, and some of these surface treatments may contain VOCs, volatile organic compounds, which may be concerns, safety concerns. In addition to that, we need to consider the life cycle of some of the solutions that are being considered, and that speaks to the economic considerations. Service record is a very important concern. Older systems that have a proven history of use are easy to qualify because of the fact that they have a history. Newer technologies, as they come about, it's a little more challenging to be able to establish that record, that performance record. Appearance is also very important. A lot of these surface treatments, when they're applied on structures, they may change the appearance of the structure. So obviously this is something that needs to be considered, particularly with owners that are very concerned with the aesthetics of the structure that is being treated. The construction quality monitoring is very important, of course. It speaks to the quality assurance and quality control during the installation of the systems. It's very important to perform these tasks to ensure that they perform as intended. Environmental considerations are already touched on, particularly some of these surface treatments could be toxic when they're applied, and they could affect the environment if they're not handled properly, particularly if the structure is in contact with potable water. There's some very important considerations where we're dealing with potable water. The type of surface treatments that can be used is strictly regulated for those applications. Compatibility and bond is also an item that is addressed in the guide, and that has to do with the fact that if we're putting surface treatment on a structure that may have already been treated, we need to ensure that there's compatibility, otherwise it would need to be removed. And likewise, bond is very important. Some of these are coatings, and they need to be adhered to the surface of the concrete, and to achieve that, special attention should be paid to the surface preparation to achieve the best possible bond. Durability and performance, I think we've talked a little bit about that already, but the success of these systems is predicated on the longevity of the systems, particularly when exposed to the specific environment that we may be dealing with. Safety requirements are dealt primarily during the installation of these systems and resistance to chemical attack. So prior to this, these requirements are applicable, as I said earlier, to both surface treatments and electrochemical treatments. So we jumped the gun a little bit, and David spoke about electrochemical treatments. So now I'm going to get into surface treatments. Basically, the objective of surface treatments is to prevent contaminants and moisture from coming through. And if you can reduce the moisture, it follows that you should be able to reduce the corrosion rates, particularly if the exposure is not quite at the point of reaching corrosion thresholds or contamination thresholds. We also want to impede the ingress of any type of contaminant that might contribute to the corrosion process, such as chlorides, chemicals, and other carbonating agents. Uses include vertical surfaces, horizontal surfaces, and precautions need to be taken when selecting these systems, particularly for items that we've talked about already, but it's important to re-emphasize them. Safety is one of them. Compatibility is another one. And durability of these systems is very important to understand. The properties need to be matched with the application that we're considering, exposure to the various environments and the applications of the systems. And installation requirements. These include, as we will see in some of the slides following this one, various techniques for the application of these surface treatments. Some specific performance characteristics that are addressed in the guide include water permeability. We certainly want surface treatments that are highly resistive to water permeability. Moisture vapor transmission is something that on the face of it you would think you want to have very little of it, but in reality, as we will see, it's something that we don't. We actually welcome vapor transmission through some of these coatings, so that they're able to stick to the structure a lot better. Crack bridging is something that we always look for. Some of the coatings in some of the surface treatments that we'll talk about don't have the ability to bridge those cracks, particularly if they're live cracks, if they're constantly changing and moving. Very few of these surface treatment techniques or technologies are able of producing good crack bridging, as we'll see. Skid and slip resistance is important, particularly if we're treating slabs and horizontal surfaces. It's important to consider those characteristics for the surface treatment. Appearance, I've already mentioned it. It's very important to the owners. Carbonation resistance and volatile organic compound characteristics. Again, this is something that as the material cures, when you place it, there's going to be some of the chemicals that are going to exude as the material is curing, and those need to be addressed, and we need to be conscious of that as we are allowing the coatings to achieve their performance status. The guide breaks down the surface treatment classifications as follows. We have penetrating sealers. We have surface applied corrosion inhibitors. We have surface sealers, high build coatings, elastomeric coatings, and overlays. We'll see those in a lot more detail. Penetrating sealers, as the name implies, consist of basically applying a coating on the surface and allowing it to migrate to a certain depth, penetrating the porosity of the concrete. They remain near the surface, and some of them are water repelling. And they don't have the ability to bridge cracks, although there may be some very, very small hairline cracks. Maybe some of the coating will penetrate into those cracks and will provide some capability to keep the water or the moisture out. The depth of penetration varies depending on the manufacturer and the type of material that is being used. It doesn't necessarily alter the appearance, except that may change the color a little bit, as can be seen in that lower photograph right here. This is an application on a horizontal deck, and as you can see right here, this area has already been coated, and the technician is applying it by roller. These materials include silanes, siloxanes, epoxies, and methacrylates. They prevent the intrusion of water, chlorides, and mild chemicals. This is primarily how they perform. Some allow vapor diffusion, and as I said earlier, vapor diffusion is good because what you don't want to happen is that water accumulates at the interface between the coating itself and the substrate. When that happens, bad things happen. Some cautions that we need to be aware of include proper surface preparation. You need to have a well-prepared surface, clean enough to allow the material to actually penetrate into the pores of the substrate. And some of these penetrating sealers are affected by UV, meaning that eventually they could become chalky and discolor. Most of them are colorless, so it's not a big deal, but UV could affect some of these penetrating sealers. Surface applied corrosion inhibitors are treated in this section because they're topically applied. They could be considered topical treatment or a surface applied protection system. They're topically applied. They need to migrate into the steel, and they're theoretically placed on the surface to a certain amount, and they migrate through the concrete until they reach the level of the rebar. Chemical reaction takes place, and it inhibits corrosion. The effectiveness in life expectancy of these systems is debated and unknown. Nonetheless, they're being used, and it is important that when owners or specifiers select to use these technologies, that they clearly understand that they need to specify how the success is monitored. How are we going to monitor the performance of the system? How do we know that we're getting the proper dosage, reaching the level of the rebar, and what technology or what techniques are going to be used to actually demonstrate that? Surface sealers are not much different than penetrating sealers, but basically they build on the surface of the concrete itself. These are typically 10 mils or less, and they don't have very good crack bridging capabilities, but they include epoxies, urethanes, methacrylates, and acrylic resins. They operate by reducing the intrusion of water and chlorides, and in some cases mild chemicals. That's their purpose. Eventually, they are effective in preventing probably new contaminants from coming through. What needs to be taken into consideration with any one of these surface treatments is that when we're dealing with structures that are already contaminated, there are species in the concrete already which could support corrosion. And although these surface treatments will mitigate the moisture ingress and might reduce the corrosion rates, they will not resolve the entire issue with contamination within the concrete. High build coatings include coatings that are range from 10 mils to 30 mils in thickness. They do alter the appearance of the structure or the surface somewhat. They adhere to the surface. They have some penetration into the concrete, but primarily to the extent that they actually grab to the concrete. So a good bond is important for these type of coatings. These include these materials that you can see right here: acrylics, alkyds, styrene, butadiene, copolymers, vinyl esters, chlorinated rubbers, urethanes, methacrylates, silicones, polyurethanes, polyurea, and epoxies. There are others, but these pretty much cover the majority of the polymers that are used for these coatings. They're used both for protective and decorative purposes. They do alter the surface, as I said earlier, and they may be applied with a variety of techniques: brush, roller, squeegee, spray. What you see in this lower left picture right here is a squeegee actually spreading the material on a horizontal surface. In some cases, these coatings are treated to increase their skid resistance and their slip resistance. And what you see here is, in this picture in the middle, is sand being broadcasted onto the coating itself using a pressurized sand pot right here. Now, I spoke earlier about the possibility of damage, and I want to point that out. In this picture on the right-hand side, you can see that some of the coating is delaminated, and that occurs because there was poor surface prep, and also there's a possibility of vapor migration, bringing moisture, letting the moisture accumulate at the interface between the coating and the concrete, allowing blistering and damaging of the coating, or delamination, as you can see right here. This is another picture showing the same scenario for elastomeric coatings. Again, elastomeric coatings are surface treatments. They're a little thicker than the high-build coatings that we spoke of earlier. They're anywhere from 30 mils to 250 mils in thickness. As the name implies, they're pretty elastic. They're flexible. They have a greater capability of bridging cracks. It's imperative to understand that if these coatings are going to be used on slab on grade, that there's a possibility of water vapor actually migrating up and creating this blistering, which not only damages the coating by water accumulation, but in areas of cold weather, you may get freeze-thaw damage to the concrete itself by allowing the water to accumulate in between the coating and the concrete. Overlays, following the same thing, are products that are 250 mils or greater in thickness. This can be bonded or unbonded when they're placed on the substrate. They include polymer concretes, Portland cement concretes, epoxies, polyesters, polymer modified concrete, and other hydraulic cement concrete overlays. There is definitely a change in appearance of the structure. And other considerations that need to be taken into account is the dead load weight and the possibility of cracking when these are allowed to dry too quickly. They need to be cured. They need to be treated as regular repair. But surface preparation is critical. If cracking is expected, if movement is expected, many times that would make you choose an unbonded overlay in cases like that. Some of the overlay systems in the marketplace include unbonded systems like asphalt, asphaltic concrete, or concrete itself. These are typically used on bridge decks and other type of plaza decks and slab-type structures. And then you have your bonded overlays, which include Portland cement concrete, latex modified concrete, polymer concrete, and high-performance concrete. Latex modified concrete includes modifiers that allow the material to cure fairly rapidly with less water. It requires skilled installation to prevent them from drying too quickly. There's some problems associated with that. Polymer concrete, again, it's used, performs in locations where you may need to use epoxies or other types of polymers that provide higher strength, like traffic bearing structures and things like that. And high performance concrete include concretes that are treated with either fly ash or silica fume to close up the pores of the concrete itself and prevent moisture from coming through and other contaminants as well. Installation of these protective systems requires an understanding of how they're going to operate within the structure after it's been decided which type of system is going to be used. It's important to understand that the concrete repairs need to be completed, many times fully cured. Some manufacturers actually will give you time frames that may be less than the full 28 days that we typically expect for concrete to cure. So you need to follow the manufacturer's recommendations in cases like that. But we expect all concrete repairs to be completed. Surface preparation may require grit blasting of the surface, and of course for that you need to have the concrete hard enough so that you can actually perform this surface prep by grit blasting. Surface profiles are important. The adhesion of these coatings depends much on the type of surface profile you have on the concrete base. And so cleanliness is very important. The quality of the surface is very important to ensure there's proper bond between the overlay and the concrete itself. Ventilation requirements, we spoke earlier about confined spaces and conditions like that that would require concerns with safety, particularly during the installation of these systems. Temperature is also a factor that may affect the performance of the installation. It needs to be taken into consideration, particularly as some of these overlays require some cure time. The last item in the guide covers joint sealants. From the perspective of a protective system, what we want is, from these joint sealants, is to minimize the intrusion of water, contaminants, gases, and any other type of material that may actually find its way into the concrete and allow the corrosion to continue. And that includes sealing cracks, contraction joints, expansion joints, and construction joints. These are the types of joints that you can see right here. This is an installation of an injection on a crack to prevent any further migration of contaminants into the concrete. This is a joint that has been installed. And you can see some of the damage that can occur on a joint that has been poorly designed. This could not actually handle the traffic that it was intended on that structure. And you can see some of the damage right here on this photograph at the lower center portion of the slide. These are the sealing methods typically available: injection, routing and caulking, bonding, installing pre-molded seals, and applying coatings such as elastomeric coatings as well. That wraps up my portion of the presentation. Thank you.